Hello, this is Math 2270 coming to you from the College of DuPage for summer of 2020. If z equals f of xy is a function of two variables with continuous first partial derivatives in region R of the xy plane, then its differential, studied in COD Calc 3 anyway, is dz is equal to, this is the partial of f with respect to x times dx plus a partial of f with respect to y times dy. In the special case, when f of xy is equal to a constant, that means z is a constant. The differential of z is going to be 0 because z equals f of xy is a constant, and so we get 0 and this expression. So in other words, given a one-parameter family of functions, f of xy equals c, we can generate a differential equation by computing the differential of both sides. For example, if we have this, then the partial with respect to x is this, and the partial with respect to y is this, and the other side is going to be 0. It also sometimes works the other way. This is what exact equations are. Sometimes this ends up being an exact differential, and we can reverse this process. So here's our definition. A differential equation m dx plus n dy is an exact differential in region R of the xy plane if it corresponds to the differential of some function f of xy defined in R. So a first-order differential equation of this form, again m dx plus m dy is equal to 0, is said to be an exact equation if the expression on the left-hand side is an exact differential. We learned criteria in Calc 3 at the College of DuPage for when this would be an exact differential. So if m and n are continuous and have continuous first partials in a rectangle defined by this, then a necessary and sufficient, that is if and only if, this be an exact differential is the partial of m with respect to y is the same as the partial of n with respect to x. Now the proof of this, because it is if and only if, is straightforward in one way, because the equality of the mixed partials is a consequence of the continuity of the first partials of m and n. The sufficiency ends up showing there does exist a function that satisfies this whenever 4 holds. Now the construction of this is actually the same as solving a problem, so I'm not taking you through a theoretical thing. I'm just going to solve problems with you. So here we have solved this differential equation. You know what to do. Let's see how you did. First of all, we have to reorganize this a bit because it doesn't look like it needs to. We have to multiply all the way through both sides by dx, and so we get this expression. So that means that this is m, and that means that this is n. So I'm going to test to see if this is an exact differential. So I will take the partial of m with respect to y. I will get 2x. I will take the partial of n with respect to x, and I also get 2x. Those two things are equal, so this is an exact equation. So that means we can take, and here I could have called it f, but I'm calling it psi, I guess. Psi of x, this is the partial of psi with respect to x is this expression, which is the m that we have. And that's the one I'm going to work with. You actually could work with either. I'm going to work with this one. And that means what I can do is I can integrate, and I'm integrating with respect to x. But when I'm integrating with respect to x, realize that y is a constant, and I get this as my answer. But instead of just having a constant, I have a constant that's a function of y. But now what I'm going to do is I'm going to realize that n had to be psi with respect to y. So this is n, but when I take psi with respect to y, I'm taking the derivative of this with respect to y, I get x squared plus h prime. Now what that means is, and this is the derivative with respect to y. Now the x squareds will cancel out, so this is going to be h prime of y is 2y plus 1. I can integrate that. I get y squared plus y plus c. And so this is what I get for my solution. Notice that this is an implicit solution, and I do set this equal to 0. So here's another problem for you to do. You know what to do. Let's see how you did. This problem is similar to the other one. The big difference is that I gave you an initial condition, and I also asked you to find the interval of validity. Well, we found a solution last time, so you apply the initial condition. You should have gotten C to be 6, and that means this is what your expression looks like. We have to solve this explicitly for y, but this is a quadratic, so we have done this before, painfully, but we've done this before, and this is the quadratic formula applied to that quadratic in y. Now we still have a plus or minus, and I do some simplification here. You really should check and work through that. But that's what we use to figure out, oh, which one do we have to use? Is it the plus or the minus? Well, y is minus 3 when x is equal to 0, so you can do the calculation. You find out, oh, it has to be the minus, because I have to have a minus 1 minus 5 over 2 to get minus 3. So that is my explicit solution. Now, I have to make sure that what's underneath the radical is greater than or equal to 0. Now, it turns out that the roots of this are rather nasty. This would not be a good test problem. The roots are at minus 11.8 and minus 1.39 and change. And this is what we get, but that has to be bigger than 0. So that says that there are 2 potential intervals of validity, but only one of them has the initial condition there, and so this is the interval of validity. Now this is a much better test problem. It's tamer. You know what to do. Let's see how you did. Okay, now you do have to clean this up in 2 ways. You have to change this. This is dy dx. You have to multiply all the way through by, actually it's not dx, it is dt, because t is your independent variable. So we're multiplying all the way through by the dt. That means that, oh, and the other thing that we have a minus sign here, and in our general form we have a plus, so you have to compensate for that. So this results in being m dx plus n dt, or excuse me, it's m dt plus n dy, and so that tells us that this is what m has to be and this is what n has to be. You really want to think through that and make sure that you understand that. But then I'm going to test to see, is this an exact equation? Well, I take the partial with respect to y and the partial with respect to t. Those two are equal. That means it's good to go. If you're not careful with this sign, you can get the wrong answer there, and that can lead you very much astray. So it is exact. We're going to integrate the first one, which is this one, and we're integrating this with respect to t this time. So when we integrate this with respect to t, again, you should make sure that you do get these answers for your integrals, but you get this as the integral, and your constant is really a function of y, because I integrated the one with t. So if I differentiate both sides with respect to y, I'm going to get h prime of y, and this expression, and I'm going to set that equal to n, which is this expression, so the logarithms cancel out. I know that h prime of y is minus 2, h of y is minus y when I integrate that. Okay, so then I go back and I put in h of y in there, and actually I should have said this is minus 2 y plus c. I did not say that. I should have. And so there's a c involved in this, so this is equal to c. Now I can use my initial condition to figure out that c has to be minus 25. And you again should check that you do that. So now I can solve this for y this way. And now I've explicitly solved it for y, and now I want to find the interval of validity. So I find out I can't have 0 in the denominator, so I find out the points I have to avoid, and I have to avoid plus or minus square root of e squared minus 1. Now, when you think about this, this splits the real number line into 3 possible intervals of validity. but the one that has our initial value in it is this one. There is a discussion of integrating factors sometimes in these books. It's cumbersome, difficult to remember, and does not work on a one-for-one basis, and I'm choosing not to hold you responsible for this at this time. And when I say at this time, in this course. When testing an equation for exactness, make sure it's in precisely this form with the pluses where they need to be. Sometimes I will give you a differential equation that will look like this, and that means you have to move things to one side and fix everything up, so you rewrite it. I chose to do this after the linear things because in Zill's later editions he actually made that change. Congratulations, you have found the embedded 24-hour quiz. I am going to double the point values for this, and so this is going to be 20 points. Take-home protocols apply. And you may want to pause the video because this is the only place where this problem is stated. I provide an answer sheet for you to complete. So you're to solve explicitly this differential equation with that initial value. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of others.